can we start now?
Yeah.
Okay, so this week we have Dan who will tell us about the Hofer-Wysocki-Zehnder conjecture on two or infinitely more.
Okay, well, thanks a lot for the invitation. It's a pleasure to be here. Yeah, I always love the Institute. Okay, so I want to talk about the following conjecture. So this is due to Hofer, Wysocki, and Zehnder, as Shira was saying, from a paper from, it was accepted in 2001. So I'll fill in the actual conjecture in a second. Let's do a little bit of notation first. I mean, I think everyone here actually knows all this, but it's good to just fix some notation. Lambda is going to be a contact form on a 3-manifold. So yes, I'm in dimension 3. So this means that lambda wedge d lambda, say, is positive. I'm only interested in oriented manifolds here. So I'm going to be interested in the kernel of lambda. And I'm also interested in this. So this is the associated contact structure. And I'm also interested in this vector field, the so-called Rave vector field. Which is in the kernel of lambda, and the closed orbits of the Rave vector field are called Rave orbits. Okay, so now I can state the conjecture. Maybe, unfortunately, I have to lower the board to actually reach it. But let me know if you want to see the notation. So the conjecture says that if I have a contact form on the 3-sphere, with associated contact structure being standard, has either 2 or infinitely many simple Rave. Okay, so any questions about the conjecture or the notation or anything like that? So maybe I didn't say what standard is. There's a contact form just given by restricting the standard primitive of the symplectic form on R4 to the boundary of the standard ball. That's the standard contact structure. Or if you prefer, it's the unique tight contact structure on X3. And, I'm always assuming my contact structure is given by taking the kernel of lambda. So that's the conjecture. Let me just make a remark. So HWZ proved this for what are called Kupka-Smale contact forms, generic condition. So I'm not going to write the definition of Kupka-Smale on the board. We won't use it at all in the talk. But anyways, it means that the contact form is non-degenerate, and it means that the stable and the unstable manifolds of the hyperbolic orbits intersect transversely. And maybe what's more interesting from the point of view of this talk is the difference between generic versus non-generic. So maybe the main takeaway is that the HWZ condition already holds for generic contact forms. So with this conjecture, we're really just interested in, what kind of strange things might be lurking in the non-generic situation. And that was actually what interested me in the problem. I mean, maybe let me say a little bit more about this. So actually, this was a question that I got interested in when I was a postdoc at IAS in 2014. So I'm very happy to be able to talk about it here at IES. And precisely what it interested me was exactly that point. Namely, normally in such theorems, one usually at least assumes that the contact form is non-degenerate. Kind of analog of the Morse condition if you're not used to seeing this. And then, the thing that was interesting to me in 2014 is how do we come up with tools that don't require any kind of non-degeneracy for the contact form or anything in order to prove something like this. Okay, so the theorem that I want to talk about today, it's joint work with Umberto Arenovich, Mike Hutchings, and Hui Liu says that in fact, if I have any contact form on any three manifold, then this always has two or infinitely many orbits. As long as the Chern class of the contact structure, so this is just the first Chern class, you can view this as a complex vector bundle, is torsion. So in particular, this verifies. So the first remark is that the theorem certainly implies the HWZ conjecture. I mean, the reason is that the first Chern class is taking values in the second cohomology, and that's certainly zero for the three sphere. Any questions on any of that? But you get something more in the case of S3. It's telling you that you don't need anything like the contact structure being standard. That doesn't have anything to do with it. Yeah. Were there questions or anything?
Is there like this C1 condition is it or that?
Yeah, great question. Probably not. However, let me state the second remark. So in general, so for a general three manifold, so if you have any closed three manifold, the case of two orbits is now well understood. So let me give you some examples. So for example, what you learn is that Y has to be a lens space. And you learn a lot more. You learn that the orbits bound surfaces of section. We'll return to that in a minute. I don't want to get too into the other criteria. But at any rate, I wanted to mention this partly in relation to the previous question. So what I'm saying is that if you have any closed three manifold, 2 is the minimum number of orbits. That's also something that's known. And if you have exactly 2, the manifold has to be a lens space. In particular, the Chern class has to be torsion. So you're asking about what one expects. So it is very likely the case that lens spaces are the only ones with finitely many orbits, and in particular, the only manifolds for which these 2 or infinitely many, for this 2 or infinity phenomenon could hold, should actually satisfy this condition. So the other conjecture would then just be that you know, if you're not a lens space, you have infinitely many orbits. That's what one expects.
And do they give the tight structures on lens spaces there?
Yes, they do. Yeah, we could add that too. They give, you know, the standard, the universally tight. The standard one on the lens space. That's right. So for example, actually, so if you have like one of the over twisted contact structures on S3, combining these two theorems implies that every contact form has infinitely many orbits. But it certainly remains an interesting question to prove. You know, I think the conjecture should be that if you're not a lens space, you have infinitely many orbits. Remains an interesting question. So there's another corollary. Oh, and I guess I should just say, I said this is well understood because it's not the point of the talk, but part of this was actually previous work by the same group of authors. So this is kind of part of our program to understand degenerate contact forms. So you also get a corollary. So the following was of interest in Finsler geometry. So you get the following corollary. So any Finsler metric on S2 has two or infinitely many closed geodesics. So this was a kind of an old question. Maybe I don't want to talk too much about this just because we only have a finite amount of time, but you know, maybe one thing to say is that so Finsler metrics, you know, they're like Riemannian metrics, only more general. We're just requiring that the unit tangent space is a ball. Sorry, is convex. And a kind of an old theme in Finsler geometry is to find to understand what in Finsler geometry is like the Riemannian case and what is not. So in the Riemannian case, actually every metric has infinitely many closed orbits. So this is had attracted interest for a while as a kind of interesting difference from the Riemannian case. That you can have Finsler metrics with just two closed geodesics is an interesting difference between Finsler geometry and the Riemannian case. And yeah, so anyway, so this has interest in Finsler geometry. For the higher genus surfaces, actually our results also apply, but it was already known that those always have infinitely many.
So do you mean simple closed or just closed?
Maybe I don't quite want to use the word simple. Maybe primitive would be better. I'm not claiming that they don't intersect themselves, but I don't want to allow, you know, multiple covers. Yeah. When I write simple in the case of Rabe orbits, well, a Rabe orbit can't intersect itself anyways. So simple just means, I mean, I'm just trying to rule out what would be a silly thing. Like strictly speaking, if I didn't put some adjective, once I had a single Rabe orbit, I would have infinitely many because I could just go around it a bunch of times.
You're saying you could have precisely, well, you could have two. You have an example with exactly two.
Yeah. So there's a famous example due to Katak with exactly two primitive geodesics on the two sphere. A symplectic geometer would just call that the example of an irrational ellipsoid. So there's a close connection between the two. Okay. Okay, so any more questions about any of this? I'm happy to answer questions. Okay, so that was supposed to be part one. I don't think I actually included the one. That's okay. It's implied by the two. So part two is then going to be the idea of the proof. So I first want to say the idea, and then I want to give some details. Okay, so the basic idea is as follows. So the goal, our kind of goal, is to find non-degenerate contact forms lambda n converging to lambda with global surfaces of section Sn such that the SNs converge to a global surface of section S infinity. Okay, so that's a slogan. I want to focus on this for a minute. Okay, so that's an important slogan for the proof. I definitely want you to understand it. Maybe so that in order for you to understand it, I should first say what a global surface of section is. So some of you probably familiar, others probably not. So what is a global surface of section? Sorry, I'm just trying to figure out what to do with the sweatshirt here. Okay, so I'm going to draw you a picture of a global surface of section for a flow, and then I'll tell you more about it. So okay, so here's a picture. It's maybe good to keep in mind. So this is a global surface of section, let's say for a flow. Okay, so this is the kind of picture people draw. So the key points, so maybe this is some Sn. So the key points are the boundary of Sn is a periodic orbit. And then another important point is every flow line hits the global surface of section forwards and backwards in time. So flow line other than the boundary hits, so is transverse and hits the interior of Sn forwards and backwards in time. Okay, I'll pause and see if you have any questions. But at any rate, the upshot of why we actually care about these is that if I have a global surface of section, I can define a return map from the interior, so I'll call it P, from the interior of Sn to itself. And let me try to write this a little bit more clearly. I can relate periodic points of P to periodic orbits the flow. Okay, so maybe I'll stop there in case you have any questions. In any event, the good buzzword would be like dimensional reduction. So the picture I want you to have in mind is, remember I have these lambda ends converging to lambda. I have the rate flow for lambda n, and I want to be able to relate, well, if I have a global surface of section like this, then if I want to count the periodic orbits for the flow, instead I can just count the periodic points for this return map. So I've reduced the dimension by 1. Okay, and what I'm really interested in is the situation for lambda. So if we can get, so now I'm going to abbreviate my global surfaces of section by GSS. So if I'm given GSS for lambda, the two-or infinity conjecture follows immediately from work of, say, Franks. Since in fact P is area preserving. I'll put this part in parentheses.
Franks doesn't need the surface to be closed.
Well, Franks works for homeomorphisms. So there are various tricks that one could do, right? So there are various versions of Franks's theorem. So one thing you could do if you have a disk like this is you get an area preserving map of the open disk, and then that has to have a fixed point, by various considerations. So now you actually have a map of, so you could just look at the complement of that fixed point, and now you have some kind of map of the annulus, and then you can apply Franks's result, which says that if I have an area preserving map of the annulus with one periodic point, then it has to have infinitely many. But there are other things you could do as well. I mean, Franks's thing actually works for homeomorphisms. So you can also collapse the boundary and reduce the case of a two-sphere, if you like. So I've also been a little bit vague about genus here. In principle, this could have genus, and then it's a little bit harder to use exactly what I'm calling Franks. But in that case, it's known that as long as you have no flux, you always have infinitely many periodic orbits. So I guess the upshot is that the challenge with the paper is going to be finding a global surface of section for lambda. Once I know that I have a global surface of section for lambda, rather standard arguments imply the result there. So does that answer your question? Okay, so just a remark, I won't write it on the board. I mean, the general idea here is itself kind of inspired by work of HWZ. So HWZ proved a two infinity principle like this for boundaries of convex domains in R4. And they use a quite similar argument where first they look at non-degenerate convex domains, they find a global surface of section, and then they show that one can pass to the limit. I mean, the main challenge here is that they're really using convexity in a heavy way in their proof. We certainly have nothing like that we can appeal to. So, any further questions? So, to recap where you should be after this point then, what I've explained is that by fairly standard arguments, it suffices to find a global surface of section for lambda. And the way we want to try to find a global surface of section for lambda is to find a global surface of section for these non-degenerate perturbations of lambda and show that you can take some kind of limit. But there are many challenges with this. I mean, so to put this in some perspective, you know, I had this kind of dream of doing this for maybe like a decade, and it took about a decade to sort through all the relevant issues.
And do you really want some disk-like global surface section, or you don't care?
Right, that's a great question. So in our proof, we will always get annulus-like global surfaces of section. In principle, there's no real need for such a thing. However, our arguments actually do really heavily use the fact that the global surfaces of section are annuli. I mean, in other words, if at the end of the day I got a global surface of section with genus 50 of 11 punctures, that would be fine with me. But the only way I actually know how to get a global surface of section in the limit is to use some very special facts about annular global surfaces of section for lambda. Okay. So if there are no further questions, I want to go on to the next part of the talk, which is a kind of crash course on embedded contact homology. So it's embedded contact homology. Kind of crash course. Okay, and before I get into the details of embedded contact homology, I want to explain a little bit about how it fits into the proof. So here's the motivation for the proof. The motivation in the context of the proof. Okay, so remember, I said that in the argument we want to take some kind of limit of these global surfaces of section. And if you think about that, that actually sounds like a pretty hard thing to control. Because, for example, I was saying that, you know, the flow lines are tangent to Sn, but they could be getting less and less tangent to Sn, and then when I take the limit, you know, maybe they're not tangent to Sn anymore. There are other things that could happen. I mean, I said that this should be an area-preserving map. So in particular, these global surfaces of section have some kind of area, and the area could be going to 0. I mean, in general, it's quite a complicated problem to be able to take a limit of global surfaces of section like this. And the idea, which was already known to HWZ, is that you get a lot more control if you assume that these global surfaces of section come from holomorphic curves. So in our case, the SNs will arise as projections of Jn holomorphic curves Cn in R cross Y. Okay, so especially if you're not used to seeing this before, let me take a minute and unwind it for you because it's not such a complicated thing. I'm saying that these SNs, you know, they're living in the 3 manifold, but to actually find them, it turns out to be quite helpful to instead find some J holomorphic curve in this 4 manifold and then just project it down to Y. Okay, and this ECH is going to be like a factory for us to help us find such curves. So ECH is really useful for finding appropriate curves. Okay. So any questions about that before I get into the crash course of how ECH is good for this? I mean, when I say in the context of our proof, I mean, there's plenty of other things that ECH is good for, but for our purposes, we just want to use ECH as a kind of factory to give us J-holomorphic curves. Okay. Okay, so let me do this crash course. Okay, so this ECH, let's just do it in the case of S3, which anyway suffices for the HWZ conjecture. So let's say in the case y equals S3 for simplicity. So the first thing you want to know is that ECH of S3, let's say lambda n, is a homology of a chain complex ECC S3 lambda n. Okay, so the first point I want to make is in order to use a ECH, we require the lambda n's to be non-degenerate. So the definition requires lambda n non-degenerate. I mean, the reason I want to emphasize this point is I want to explain, why we're even taking non-degenerate perturbations in the first place. I mean, and there's actually like some interesting math there, and maybe even an interesting story. Like, there's another way one could remember. I said that the thing that had attracted me to the problem in the first place was how to develop tools for thinking about, possibly non-generic situations like a degenerate contact form. So, one thing you could try to do is actually just work directly with, my contact form lambda, try to define some kind of floor theory or something. But it seems that that's an extremely difficult problem. I mean, if you just work directly with lambda, if you just work with the degenerate contact form, various moduli spaces of pseudo-homomorphic curves, might not be describable by a Fredholm problem. And okay, I mean, here it's a little bit better because you can assume that the contact form has finitely many orbits, which helps a bit. But anyways, it's sort of a big mess if you try to work directly with lambda. On the other hand, if things are non-degenerate, you have a lot more structure. So anyways, this is kind of why we're taking perturbations in the first place. And I didn't give a definition of non-degenerate, but just think in terms of Morse theory, the non-degenerate situation is similar to studying a Morse function on a manifold, whereas the general situation would just be like studying an arbitrary function on the manifold. Okay, so any questions about that? Okay. Okay, so anyway, so that's the first part of the crash course. So what is this ECC? So this ECC is the homology. So what is this ECC? It's generated by, let's say it's freely generated. Well, let's say over Z2, that suffices for our purposes. Although you could also define it over Z by certain sets alpha I, mi, such that the alpha I are Rabe orbits and the mi are positive integers. So I'll call such a thing a big alpha, or maybe I'll call it a theta. Okay. So in other words, a generator is a set of distinct simple array of orbits together with positive integer multiplicities. So you can just think of this as like your embedded orbit and then the covering multiplicities. I used the word certain because there are some restrictions, but since we're just doing a crash course, I don't really want to get into the restrictions. And how about the differential? So the chain complex differential delta counts ECH index 1 J holomorphic curves from alpha from an orbit set theta 1 to an orbit set theta 2. Okay, so maybe I'll draw a picture, and I can always elaborate on this if people would like to see more. So anyways, a good picture to keep in mind, something like this. Here's my R coordinate, here's my Y coordinate. I have some curve. So this would be some set of orbits, theta 1. This would be some other set of orbits, theta 2. And in fact, I'm not even necessarily requiring that the curves are connected. The kind of key point is that this index 1 condition implies that the curves are mostly embedded. That's why it's called embedded conjecture. Okay, so I'm not going to define the ECH index for you, but it's some topological index. And anyways, the point is that in this homology, in this floor theory, I don't have any a priori bound over the GDIS, not even over the number of components, but I do want to consider essentially embedded curves, and they're detected with this ECH index. Are there any?
So what's the meaning of mostly?
Well, right. So it has to do with this decomposition. So in general, if I have an ECH index 1 curve, it could have many components, but it turns out that it has only one non-trivial component, namely a component that's not R invariant. So an ECH index 1 curve has this has a non-trivial component which actually is embedded, but then if it's just a curve, these cylinders could be multiply covered or something like that, but they are R invariant.
So what's the reason there's only one interesting component?
Well, it's really just because I'm only having the ECH index be 1. So if I had like 2 interesting components, I mean, think about it this way. The ECH index is supposed to bound the dimension of the moduli space. So, and I have an R action on the moduli space. So if I actually had 2 interesting components, I could shift both of them up or down, and I would get another, degree of symmetry.
Yeah.
But the way it actually works in the theory is that, basically, if I have ECH index 0 and I'm in a symplectization, I have to be R invariant like this. And everything is generally pretty non-negative and additive. So if I really had 2 interesting components, it would have ECH index 2 or something. Okay. So that's ECH is the homology of this chain complex. But remember, we're actually interested in using ECH as a kind of factory for producing holomorphic curves. And those holomorphic curves are going to come from what's called the U map. So So some important additional structure is this so-called U map. So there's a map map U mapping the ECH chain complex to itself. So it's defined similarly to the differential, but it counts ECH index 2 curves through a marked point. Let's just say we'll write it like this. So we might as well just assume that the point has height 0 and is an R cross Y. Okay, so it's just like the differential. It's just now I have a two-dimensional moduli space. I have an R translation action. Okay, so I quotient by that, but I want to count things. So I'm saying is I can fix a mark point and define a map counting curves through that mark point. And that U map is what's gonna, it's the U map curves that are gonna be useful for us for creating a global surface. Are there any questions about that? Okay, so there is a map, but I mean, that map could just be the zero map and it could be useless. That's where the next miracle comes in. And that's sort of the final part of the crash course. There's a theorem due to Taubes, which says that this homology is actually isomorphic to the Seiberg-Witten Floor cohomology of S3. And moreover, this isomorphism preserves the U map. The U map. So this is really helpful for us because the Seiberg-Witten Floor cohomology as a U module has been computed. I mean, it has, I'll show you what it looks like in a second. And in particular, the U map is highly non-trivial on Seiberg-Witten Floor cohomology. So this is going to give us an abundance of ECH curves. So in particular, so maybe I'll just say it this way. So in particular, well, I'll just maybe draw HM hat of S3 for you. It's known that HM hat of I look at HM hat of S3, I'm doing Z2 coefficients, it looks like this. And then maybe a bunch of zeros. And the U map acts as an isomorphism. Use an isomorphism. There's a grading. Since it's just a crash course, I didn't say what the grading is. But anyways, this is in grading 0. This is grading 0. So anyway, so you can see that HM hat S3 has a very interesting U module structure. So that implies an abundance of U map. Which we're going to use in the proof. So that's all I want to say about the crash course on ECH. Are there any questions about that though? So I think I started around 1240. So I might end around 140. If that worked. That's what I was thinking. So. Okay. And I mean, let me just say that, like I said, for simplicity, I stated this in the S3 case, but you know, there's a similar story for any contact manifold. Maybe at the end, you know, maybe the only interesting thing to get from that is like, where are we actually using the fact that the Chern class is torsion? As I've stated at and maybe at the end I'll get to that. So there's our crash course on ECH, and hopefully you know why it's going to be useful for the proof. So anyway, so the basic plan then is to use Seiberg-Witten to get lots of UMAP curves from lambda n that project to global surfaces of section, and then try to take some kind of limit. Okay. So if there are no questions, continue. Okay. So now things are going to get a little bit more technical. So I want to talk about limits of curves. And I also want to talk about ECH partition conditions. Okay. So the following ends up being a very key point in the proof. Okay, so here, I would say in a way, this is maybe the first kind of analytically interesting point in the proof. So here's a key point in the proof. So a kind of key challenge. Okay. So let's let Cn be counted, be a curve, be a Jn holomorphic curve, counted by the UMAP. This is part 4, part A. There's going to be a part A and a part B. And in principle, they don't seem to have much to do with each other. But in fact, they fit together very beautifully. And that was one of the key insights in the proof. Okay, so anyway, so let's say I have a Jn holomorphic curve counted by the UMAP. So general theory says that the ends of the curve, the ends of Cn, converge exponentially fast to so let me go back to this picture. So that this is, let me go back to this picture to show you. Let's say that this now was a Cn. Earlier I made this a differential curve, but I can just keep it on the board, make it ECH index 2, maybe 0 Z is and then this is like an end of the curve. So this is like an end of the curve. These are the ends. So this is a Rabe orbit. These are the ends. This is a Rabe orbit. And so just the general theory of J holomorphic curves and symplectizations due to, you know, HWZ, many others, says that not only am I converging to this Rabe orbit, but I'm actually converging exponentially fast. Okay? So let's actually write what the speed is. So let's say it's speed. At speed e to the minus rn. Okay. So anyway, so the challenge is, it turns out we want to be able to use the analytic machinery nicely of holomorphic curves in the limit. We want that this rate of convergence is not going to 0. Is not going to 0. So a basic point that you should have in mind then is, so roughly speaking, so this is roughly speaking, you want the CNs to converge to some C infinity, a J infinity holomorphic curve that also has exponential convergence as its ends. Yes. Okay, so that was going to be point A. And now I'm going to give a point B. So remember, the name of this section is limits of curves and the ECH partitions conditions. So this part A was the limit of curves. Okay, so let me try to recap this for you and see if you have any questions about it. I mean, I'm being a little bit impressionistic for time reasons here, but so I'm saying, okay, so remember, our game here is we wanted to take a limit of global surfaces of section and still have a global surface of section. So I'm saying there's some analytic machinery for J holomorphic curves, and it's going to work a lot better if the thing that I get in the limit is the projection of a holomorphic curve with exponential convergence to its ends. The reason for that has to do with weighted Fredholm theory. Maybe I don't want to say too much about that, but hopefully it's at least plausible that if the CNs are converging to some kind of object that still has exponential convergence at the ends, I can still leverage a lot of the analytic machinery of holomorphic curves to get something useful. However, what I'm saying is that there's an obstruction to that, which really could cause a lot of problems. Namely, I look at the speed at which the CNs are converging. Each one of them is converging exponentially fast, but they could be converging more and more slowly. And in the limit, I wouldn't get something that has exponential convergence, and that would be a big problem. So if you do have exponential convergence, you can use weighted Sobolev spaces. And roughly speaking, it's not quite right, but roughly speaking, what I'm saying is if you had exponential convergence, you can use these weighted Sobolev spaces, and then it is going to be like a Fredholm problem, and you can pretend more or less that you are in the non-degenerate situation. This weighted Sobolev space stuff is also kind of well known, also due to HWZ and all that kind of stuff. Okay, so are there any questions about that? Okay, but the main point I want to say is that there's no reason on the face of it that this can't be converging to zero. I mean that's just something that could happen. I mean, there's no reason that can't in general happen. However, that also gets into these ECH partition conditions. Okay, so as I said, on the face of it, this is a totally different matter. So here's a question. So what do ECH UMAP curves look like? Curves look like. So there's a story here due to Hutchings. There's an old story due to Hutchings involving what are called the partition conditions. Old story due to Hutchings. It's called the partition conditions. I'll just tell you the upshot. So the upshot is, so if you have a curve, say Cn, say it's it's a UMAP curve. There's a curve with say L ends all at the same Rabe orbit. So all at a simple Rabe orbit, gamma. Then L and even the multiplicities of each end are determined combinatorially from the rotation number of gamma. Okay, so this might sound rather abstract, but it's actually very concrete. So let me just explain in an example. So here's a nice example. So for example, so let me do an example. Let's say Cn has 5 ends at an orbit gamma with rotation number less than 1/5. So then the Hutchings machinery, this partition conditions, imply that Cn looks like this. So you have, say, 5 ends like this. So these are all at gamma. Local to gamma. And not something like this, where you wind around gamma, say, 5 times. Okay. So, hopefully the example is helpful. Let me, it's a little bit complicated, so let me go through it slowly and see if you have any questions. So what I'm saying here might almost seem too good to be true. It's not such a complicated thing, actually. So I'm saying, say you have an ECH index 2 curve, and you know, like, so let's just do this case. So you have an ECH index 2 curve, and you happen to know that it has 5 orbits, 5 ends at a simple orbit, or sorry, has, maybe I should have said this a little bit differently. So CN has ends at an orbit gamma with, so has ends of multiplicity 5. This is what I meant to say. Ends of multiplicity 5. At an orbit. At an orbit gamma. So I'm saying, say you give me an ECH index 2 curve, and you tell me that the total multiplicity of all the ends of this orbit is 5. And I know that the rotation number, so the rotation number, this is something that just is defined from the linearized flow, has some particular form, that it's less than 5. So then there's a combinatorial formula due to Hutchings, which just allows you to input the rotation number and the total multiplicity of all the ends, and it tells you the actual way that the ends look. So in this particular case, it's saying that I actually have 5 ends all at gamma rather than a single end that winds around it 5 times. Does it make sense?
Also forbids this like a 2 plus 3 type of.
Right, you're also forbidding a 2 plus 3, but it's important. It's a combinatorial formula where you have to input the rotation number. So it's important for this that the rotation number is less than 1/5. And again, I didn't define the rotation number, but it just is defined in terms of the linearized flow of the rotation. Okay, so like I said, on the face of it, these have nothing to do with each other. But the interesting thing is that the rotation number is also related to this issue of the speed of exponential convergence. Okay. So, so an interesting calculation. So in fact, this rotation number is also relates to the speed of convergence. And a calculation that's actually pretty straightforward if you actually just work through how everything is related, is that you find that ECH index cylinders, so the calculation relating these says that if the CNs are cylinders with ends of multiplicity at least 5, actually probably 3 is fine, but I'm just playing it safe. Well, let's just stick with 3. With ends of multiplicity at least 3, then the rate of exponential convergence does not go to 0. Okay, so I don't have time to show you the calculation, but I can at least try to explain, and that's actually why I did the example, what's going into the calculation. Okay, and I can actually give you a feel. It's actually not a long calculation, at least, you know, given what's already known about how everything relates to everything else. It's not a long calculation. And it has to do with this example, because I'm assuming in the calculation that the thing are cylinders. So that's why I did this example. If you look at, let's just do this example. If I knew that the CNs were cylinders, then that would be saying that this can't happen because this is not a cylinder, and that this does have to happen. So in other words, it would be saying that the rotation number is greater than 1/5. And then if you work out the relationship between the rotation number and the rate of exponential convergence, you'll see that that's saying that the exponential convergence is not going to 0. So essentially what happens in this is that everything is really only meaningful modulo the integers. And when things are converging to a degenerate orbit, there's basically 2 ways that they could be converging, you know, modulo the integers. The rotation number could be converging to 0, or it could be converging to 1. Like if you normalize the rotation number to always be between 0 and 1, it could be converging to 0, or it could be converging to 1. And basically, this is the bad case where if you work out the relationship between the rotation number and the exponential convergence, if the rotation number is actually converging to 0, like in this case, I get something bad. So what happens is that if I happen to know that I have cylinders, then it turns out that my rotation number, you know, is converging to 1 when I normalize it to be between 0 and 1. And if you work out what that has to do with the exponential convergence, it says that the exponential convergence is going to persist. Okay, so anyways, so that's some kind of principle. And then in my remaining 2 minutes, I just want to kind of put it all together and say what the challenge is. So, part 5 is putting it all together. So hopefully I've convinced you then that we want cylinders. It's really important that we have cylinders because of this kind of weird thing about exponential convergence. From the ECH UMAP. And I'm going to put this in quotes because, you know, I would say that to this point, I've probably explained about 10% of the paper. In other words, it's definitely like quite hard going from here. So, okay, so you want cylinders from the ECH UMAP. The problem is that the UMAP curves definitely need not be cylinders. Need not be cylinders. I mean, as I was saying, when I drew them, there's no a priori bound on the genus or anything like that. So there's no particular reason why they should be cylinders. Now, much of the paper is devoted to techniques for showing that they actually have to be cylinders. So the basic idea, is that there are infinitely many UMAP curves for each CN and combinatorial techniques and some lengthy and let's say probabilistically.
Do you mean for each lambda?
For each, yeah, sorry. Oh, for each lambda. Thank you. Yes, for each. And so we show using we show kind of that probabilistically, most actually are cylinders. And this is where we use that the Chern class is torsion. So unfortunately, I won't be able to explain this. In fact, this was more or less where I planned on stopping, but maybe I just give a little feel for it. So I guess to recap then, what I've hopefully convinced you of is that it's useful for some kind of subtle reasons that the ECH curves are cylinders, but now the problem is that why should the UMAP curves be cylinders? And well, a lot of our paper is devoted to techniques for trying to analyze the topology of the curves, but maybe the basic principle that I'm trying to say is that for each lambda n, we actually have a lot of curves, because if you look at the Seiberg-Witten-Floer cohomology, right, there's infinitely many non-trivial UMAPs. So we do something like consider a larger and larger sequence of curves and try to understand the probability that a curve in that will be a cylinder. And we show that the probability is actually 1. But that uses this Chern class assumption basically because, it gets fairly complicated, but the basic point is that when the Chern class of the context structure is torsion, if you look at the index formula, then the index, the Fredholm, like the Fredholm index of these UMAP curves is also 2. So if you look at the index formula, well, it gets a little bit complicated, but the only term in the Fredholm index that doesn't see the topology, you know, the index formula has like the Euler characteristic, the Conley-Zehnder index, and the Chern class term. And if we can just ignore this Chern class term entirely, then we can play much better games about the fact that these curves have to have Fredholm index too, and playing the Conley-Zehnder indices off each other. And so, yeah, so that's sort of the point. So anyways, I think I'll stop there. Hopefully that at least gives you a flavor for the arguments.
Thank you very much. Any questions?
Yes, so just so to prove this ECH modular space converge, like only C0 convergence, do you need non-degeneracy?
You mean if I wanted like a sequence of curves and I just want to know that it's going to converge to something?
Yeah.
Well, I mean, in general, right. I still have a reasonable version of Gromov compactness, like at least in this kind of setting, I have exponential convergence. So you're saying if I didn't have exponential convergence, you know, would I still get something? Yeah, I mean, I think you still have various versions of Gromov compactness that you could do, but I mean, in general, you get those kind of statements where you could have bubbling and stuff.
Don't you also get a surface of GSS? Like even if you don't, you know, assume the non-degeneracy, like you get C0 convergence, but still the boundary, you know, ends converge to PR, you know, orbits.
Well, you get something, but in general, it definitely might not be a global surface of section. I mean, to put this in some perspective, it's a conjecture actually that every ray flow has a global surface of section. So one thing you could try to prove is that every ray flow has a global surface of section. And that would also imply this 2 or infinity conjecture, because you could still use Franks's thing. And it's known that Kupka-Smale ray flows actually do have global surfaces of section. So that's a relatively recent result. And that is a generic condition. So in principle, one could attempt to do a similar thing where, you know, you find a global surface of section for a family of, you know, you find a family and try to take some kind of limit. So if you could do that, then you would prove that every ray flow has a global surface of section. But hopefully you believe that I don't know how to do that, because if I did, then I would do it. And the problem has to do with these subtleties of exponential convergence. Another subtlety is what one could call the Hofer energy. Like I was saying the area of the curves could go to 0, but if the boundary of the curves are getting more and more complicated, that gives some kind of problems too. I mean, you don't necessarily, you need some kind of arguments that the ray orbits at the boundary themselves are converging to some kind of ray orbit. So.
Yeah, it sounds a little bit like the crazy curves of Fish and Hofer.
Right, well, yeah, I mean, Rohill and I wrote this paper with these crazy curves where it's a
Yeah.
similar, with the paper with Rohill, it's more like the crazy curves.
Yeah.
Yeah, but actually in this paper, we're able to completely work in the standard kind of analysis, not in the Farrell analysis, but with the paper with Rohill, indeed, we need to Farrell techniques.
Yeah. Does it matter does it matter what perturbations you take or just any non-degenerate?
No, we take some special perturbations, actually. Yeah, so we have a kind of perturbation lemma for the kind of perturbations that we want to take. So basically, you could imagine if you have a degenerate orbit that has this rotation number, then it turns out it has to be a rational number, say A over B. And basically, we show that there exists a perturbation such that when you perturb, the only new orbits arising from it are all B-fold covers of the original orbit.
Oh.
Or the kind of,
Yeah.
so that's some kind of special perturbation. Yeah.
Right.
Oh, wait, I think there was a question, but maybe we also need to clear out, but I can stick around. Did you?
Yes.
Yeah.
So I guess I have two questions. One, is the standardness of the contact form used anywhere in your proof other than like in the original 2011 proof for the generic Krupke-Smale contact forms?
No, so in our proof, it's only relevant that the Chern class of the contact structure is torsion, which happens automatically over S3. In Hofer's proof, which I don't know if I stated it correctly, but that was from 2001, their proof. In their proof, the standardness is actually important because the way they get the holomorphic curves in the first place, as I recall, is by putting it in like CP2 and doing some kind of neck stretching type of arguments. And that for there, the standard contact structure is important. For us, we're just using this Seiberg-Witten thing, which doesn't even see the contact geometry of the contact structure at all, so.
And I guess my second question is it necessary for this proof that like with probability 1, a curve is a cylinder? Like, do you need almost every single curve to be a cylinder, or just would having some curves be cylinders?
Yeah, if you just had some curves, it would be fine. I mean, there are these kind of subtleties that have completely glossed over along the lines of what Shira was asking about, where you want to work up to a fixed action and, things need to kind of be, reasonable. But no, you just need one of them, but I don't really know how to find one of them without finding all of them. That's right. I guess what I'm saying is that you can imagine that in general, it's a hopeless mess, but you do have infinitely many ones for each one. So if you work really hard, you can find one.
You have probability 0, but you would have 0 chance at some point.
Right.
So we think again?